Hello, good morning. I am SEEMA GARG, Associate Professor in Chemistry, SPC Government College, Ajmer. Today, lecture 11, video 73. It is regarding for carbocation reactive intermediates. It is for B.Sc Part 1, Organic Chemistry, Paper 2. Generally, 6 types of reactive intermediates are encountered in various organic reactions. Carbonium ion, carbocation, carbon anion, free radicals, carbenes, arynes, and nitrates. A carbocation is an ion with a positively charged carbon atom. Among the simplest example is it is a methanium ion. Properties of carbocations: it forms due to heterolytic bond cleavage. Structurally trivalent compound. It having empty p orbital, sp2 hybridization. It having 120-degree bond angle, electrophile compound. It is a electrophile. It means electron deficient. The different kinds of carbocations: primary carbocations, secondary carbocations, tertiary carbocations. Primary carbocations. In a primary carbocation, the carbon which carries the positive charge is only attached to one other alkyl group. It is a ethyl, propyl, isobutyl, etc. Secondary carbocation. In a secondary carbocation, the cation, this carbon with the positive charge is attached to two other alkyl groups which may be the same or different. See here, propyl secondary, butyl, isopentane, tertiary carbocation. In a tertiary carbocation, the positive charge carbon atom is attached to three alkyl groups, which may be any combination of same or different. Formation of carbocation. Solvolysis. Solvolysis is a type of nucleophilic substitution reaction or elimination reaction where the nucleophile is a solvent molecule. The solvolysis of tertiary butyl chloride in an SN1 reaction, it involves the formation of tertiary carbocation. See here, alkyl halide, it will dissociate into carbocation and nucleophile. See here, intermediate, carbocation intermediate formation. By arene diazonium salt. Here, this arene diazonium salt also form carbocation. It is also again SN1 mechanism. The greater stability of arene diazonium salts compared with alkane diazonium salt to be related the difficulty of forming aryl carbocations. Even the gain in energy with having nitrogen as the leaving group is not sufficient to make aryl cations form readily. Solvolysis of arene diazonium ions in water does proceed by an SN1 mechanism. From superacid. From superacid means trifluoromethane, sulfonic acid, and fluorosulfuric acid. Magic acid has a low nucleophilicity, allowing for increased stability of carbocations in solution. Many tertiary cycloalkyl cations can also be formed in superacidic solution. One such example is the 1-methyl cyclopentyl cation, which is formed from both the cyclopentane and cyclohexane precursors. Protonation followed by dehydration of alcohol. It is a very common reaction, dehydration of alcohol. Here, first step involves the protonation of the alcohol by an acid, followed by loss of water to give carbocation. In second step, actually we are not concerned. After that, we will get alkene molecule. We are interested in formation of carbocation. Protonation of alkenes. Here by acid or base, acid and base reaction, protonation of alkene to generate the more stable carbocation. See here. In step 2, we will get the substituted product or addition product. Protonation of carbonyl compounds. Here, protonation of carbonyl carbon of the carboxylic acid forms carbocation, and nucleophilic attack of alcohol molecule to form oxonium ion. See here. Stability of carbocations. Increasing substitution by carbon stabilize carbocation. Alkyl groups when methyl, ethyl or weak electron donating groups, and thus stabilize nearby carbon cations. Most substituted carbocations are more stable. Primary carbocations are highly unstable and not often observed as reaction intermediates. Methyl carbocations are even less stable. See here the order of stability. Electron releasing and electron withdrawing. In generally, electron carbocation is very electron poor, and thus anything which donates electron density on the center of the electron poverty will help to stabilize it. Carbocation will be destabilized by electron withdrawing group. See here. Presence of double bond. The positive charge is delocalized around the aromatic structure. This delocalization of charge results in stabilization. As a result, benzylic and allylic carbocations are significantly more stable than even tertiary alkyl carbocations. See here, this allylic and this benzylic carbocations are stable due to the presence of double bond. Presence of heteroatom also helps in stability of carbocation. Heteroatoms such as oxygen and nitrogen are more electronegative than carbon. This is due to the heteroatoms are electron withdrawing groups by induction. They are electron donating groups by resonance, and it is this resonance effect which is more powerful. See here, this is secondary is more stable compared to tertiary. Means here on third position, means on second position, it is more stable than compared to third position. Next, hyperconjugation. The interaction of electrons in a sigma bond with an adjacent empty non-bonding p orbital, in general, greater the number of alkyl groups attached to the positively charged carbon atom, greater is the hyperconjugation and greater will be the stability of carbocation. Aromaticity. Electrophile attack the benzene ring or aromatic ring leads to the formation of a resonance stabilized carbocation known as arenium ion. See here, it is arenium ion formation, and this arenium ion is due to the delocalization or resonance structure, it is stabilized. Thank you very much.